We have an absolutely awesome question here. A little bit of calculus, a little bit of proof by induction, a little bit of everything. So let's tackle it together. Say we've got the equation or the function y of x is equal to x times e to the 3x. We're first asked for 2 points, nice and simple, to solve for dy dx. This will help us a little bit in parts b, c, d later on. So to do this one, we see that this function is a product of two other functions, x and then e to the 3x. So this just becomes a little power rule. Power rule, as a reminder, is u v prime plus u prime v. So we take the derivative of the first term, in this case x, is just 1. I'm going to write it in for the case of, or for the sake of simplicity and completion, 1 times the second function, e to the 3x, plus the first function times the derivative of the second function. Derivative of e to the 3x is 3e to the 3x. So that gives us e to the 3x plus 3x e to the 3x. Part A, nice and simple, 2 points. Now is where things get interesting. For part B, prove by induction that the nth derivative of the function y is equal to that expression. We want to prove by induction that the dn of y dxn is equal to n times 3 to the n minus 1 e to the 3x plus x 3 to the n e to the 3x. All right, how do we do this? Proof by induction always has 3 steps. First step of the proof by induction is to show that this works for the base case. And usually what this means is that you let n be the simplest number it possibly can be and just show that the proof or the thing that you're trying to prove even works in the first place. So for this case, we're going to plug in n equals 1, so the dy dx, which you notice is actually the original term we have up here, so it should spit out the same value. That's why it's always helpful to check your work along the way. Well, let's plug in an n for every time we see, or 1 every time we see an n in that expression. 1 times 3 just goes away. I'll write it anyway. 1 times 3 to the 1 minus 1 e to the 3x plus x times 3 to the 1 e to the 3x. Well, let's simplify this out. 3 to the 1 minus 1 is 3 to 0, which is just 1. 1 times 1 is 1. So this just leaves me with an e to the 3x plus 3x e to the 3x. Those two are identical. So we've shown that this works for the base case. Actually, you know what? Let's go over here. Part 2 of the proof by induction is to assume that it works for the k case. So if I plug in a random number, let's call it k, into this, we're going to assume that it works. So I'm going to rewrite this as assume that this is true for the dk of y dx to the k, which would leave me with a k times 3 to the k minus 1 e to the 3x plus x 3 to the k e to the 3x. So that's basically the entire step. Now, if we assume this is true, what we have to do is we have to prove that this works for the k plus 1 case. This is always the hardest step, or this is the most important step in the proof by induction problem style. To do this, to show that it works for the d to the k plus 1 y of dx k plus 1, so the next term after the one we assumed is true, in this particular problem, and usually when they ask you to do proof by inductions with calculus or in derivatives especially, this is the main trick we need to do is to rewrite this as the dx, the derivative of the k case. We know that if we have the dky, dxk, we already have that derivative, which we are assuming is true, and if we take the derivative of that, it should give us the k plus 1th case. So that's exactly what we're going to do. We're going to take the derivative of and I'm going to use a different color, this guy, the k case that we're assuming is already true. All right, let's do that down here. So the derivative of this case, well, the derivative of the first term is relatively simple. It's just going to be k is a constant, it's just a number. 3 to the k minus 1 is just a constant, so that stays out there. Derivative of e to the 3x is 3 e to the 3x. That's the first term already taken care of. We'll simplify later. This second term here is it's basically just another product rule like we took our first derivative, but this time it's got this 3k constant leading at the front. So we're just going to leave that alone for a moment, and then we'll do a product rule. 3 to the k times, well, derivative of x is 1 times the original function plus the derivative of the second term times x. So x times 3e to the 3x. That's the derivative, or it should be the derivative of the original term that we came up with, the original k case that we're assuming is true. Now all we do is we simplify a little bit, and this should look like what would happen if we plug in a k plus 1 into this original kind of proof, or this original equation that we're trying to prove is true. Let's simplify a little bit. The k over here in this first term is going to stay, nothing to do with it, but 3 to the k times, or minus 1 times 3, we can add a 1 of those exponents together. 3 to the k minus 1 plus 1 is just 3 to the k. E to the 3x. Nothing, we're not going to change that at all. Now the second term for the time being. Can we simplify anything out? We can multiply out the 3 to the k. That might be helpful. So we get 3 to the k e to the 3x plus x 3 to the k, 3 to the k plus 1. There we go. 3 to the k times 3, 3 to the k plus 1, e to the 3x. Okay, nice. Now we need this. We need this to look like what would happen if we plugged in a k plus 1 into that original proof. So what we're going to do even here is, over on this side, I'm going to write down t to the k plus 1, y, d to the x, k plus 1, and I'm going to plug in k plus 1 into the thing that we're trying to prove. K plus 1, 3 to the k e to the 3x plus x 3 to the k plus 1 e to the 3x. We need this thing that I'm underlining in yellow to look like this thing that I'm underlining in yellow here. Now let's see how far we're come. This last term here is already good. X 3 to the k plus 1, x 3 to the k plus 1, e to the 3x. So all we need to do now is combine these two terms together. And the nice thing to do this is to realize that they both have an e to the 3x, or a 3k e to the 3x term. So let's factor that out. 3k e to the 3x. What are we left with? A k plus 1 plus x 3 to the k plus 1 e to the 3x. Because those two terms are true, we took the derivative of the k term that we assumed to be true and got this expression, which is also the expression we would have gotten had we plugged in k plus 1 into the original proof. We've proved this by induction. Nice. Whoa, look at all these fireworks. Cool. All right, we ran out of room after that super long but super beautiful induction problem. So now we can move on to parts C, D, and E of this question. What we're also going to notice, okay, is that in this particular problem, even if you couldn't solve the induction, because bearing in mind it was pretty tricky, we'll have to admit, that's only 7 of the points. There's 14 other points you can get for a total of 21 in this problem, and you did not have to do the induction problem for you to move on into questions or parts C, D, and E. So bearing in mind, if the induction stumps you, which it usually does for a lot of students, don't panic, move on, you can work the rest of the problem out, no problem. So let's do part C together. Find the coordinates of any local maximum and local minimum points on the graph of y of x, and we have to justify why they're maxes or mins. Okay, whenever we see the words max or mins, we're going to think first derivative. I've rewritten the first derivative up here already for us, which we already got from part A, and we already got a lot of information about second, third, fourths derivatives from part B. Whenever we deal with maxes or mins, we take that first derivative and we set it equal to 0. So let me rewrite that. I'm going to take the first derivative of our expression plus 3x. Oh, hold on, I messed that up. It's 3x e to the 3x is equal to 0. Solving this by hand is actually pretty simple because we can factor out an e to the 3x from both of these terms is equal to 0. And remember, just like we've learned since our 7th grade algebra classes, whenever I've got a product of two functions set equal to 0, either the first or the second one has to be equal to 0. So I'm going to set e to the 3x equal to 0 and 1 plus 3x equal to 0 and see which one of these is going to give me meaningful solutions. In this case, there's absolutely no value that I could raise e to for it to be equal to 0. We maybe know from our calculus that if I take the limit as x approaches a really negative number in this case, I might approximate 0, but for this one, there is no solution or no viable solution. So we're going to turn our attention entirely to the second binomial in this case. In this case, x is going to be, when this expression is equal to 0, x is going to be equal to negative 1/3. So here's a meaningful solution for this particular problem, which means that we know that either a maximum or a minimum is going to occur when x is equal to negative 1/3, and the question is, which one? To solve this, if you've seen some of my other videos, we're going to set up a little sign chart. It's by far one of my favorite things to do in calculus. I'm going to write the root, like we just came up with over here, draw a dotted line. Oop, I'm not going to circle it yet. I'm going to do a plus and minus sign on both sides of this, and we're going to ask ourselves the question, what sign does the derivative have on the left side of this root and on the right side of this root? To do this, the easiest points for us to evaluate are negative 1 and 0 because they're just nice, simple integer numbers. So let's start with the negative 1. If I plug in a negative 1 into this derivative, I'll write it down here, y prime. Geez, there we go. Sometimes we're writing away and can't help but make some mistakes. Hope you don't on your tests, though. If I plug in a negative 1 into the derivative, e to the negative 3 minus 3e to the negative 3. Well, the e to the negative 3's, we don't really care what they actually are because the whole point is that they're going to be positive numbers. So if I take a positive number and I subtract 3 of those positive numbers from it, I get negative 2e to the negative 3. This number is going to be negative, which means that we know on the left side of that root that the derivative will be decreasing. If we plug in a 0, let's see what happens. Y prime of 0. Will we get e to the 0 plus, 0, which is just equal to 1, which is a positive number. This is telling us that up until this specific point, the equation is decreasing. When it reaches negative 1/3, we've reached a minimum, and then it begins to increase in some other direction. So we know that x minimum, I think I misspelled minimum there. Let's try that again, shall we? Boom. See, it's one of those days, guys. I'm sorry, bear with me. Minimum. There it is. We know that a minimum occurs at x is equal to negative 1/3. It's asking us, though, for the coordinates of that minimum. So we have to go back into our original equation, which again was x e to the 3x, and plug in negative 1/3. So y of negative 1/3 equals x e to the 3x. Let's plug in negative 1/3 times e to the negative 1/3 is just going to be e to the negative 1. We can rewrite this as negative 1/3e. Based on our rules of exponents, a negative exponent can be written as positive if I bring it below the fraction. So the coordinates for this point, negative 1/3, negative 1/3e, they're the coordinates for the minimum. Part C is done. Let's move on to part D. I'm going to scroll down, do the rest of it here. It's asking us to find the coordinates of any inflection points. Inflection points, again, occur at the second derivative. Okay, so I'm going to copy down the first derivative again, e to the 3x dy dx is equal to e to the 3x. And before I really screw it up, let's do it. Copy it properly, 3x e to the 3x. Okay, the second derivative of this, dy dx squared. I could use that proof that we had earlier. I think it's more of a hassle than anything because taking the second derivative of this is pretty easy. So let's just go ahead and do it. The second derivative of this first term is 3 e to the 3x. And this second term is going to be, again, another power rule. So 3 times the derivative of this bad boy, which is e to the 3x plus 3x e to the 3x. I can then distribute this out a little bit, multiply everything out. So I end up with 3 e to the 3x, that term stays the same, plus 3 e to the 3x plus 9x e to the 3x. Okay, these two terms we can combine, so we end up with a 6 e to the 3x plus 9x e to the 3x. This is our second derivative with respect to x. Whenever we take the second derivative with respect to x, we can then, well, in this case with respect to x, we can set it equal to 0 to solve for any inflection points. So let's go up here. To set this equal to 0, let's just rewrite it to start with. That might be nice. 6 e to the 3x plus 9x e to the 3x is 0. Just like we did in part C, I'm going to factor out any like terms they have. In this case, they have a 3 e to the 3x in common. Let's factor it out. I'm left with a 2 in the inside here plus a 3x is equal to 0. To solve for x in this case, you set each of the two terms of the product equal to 0, but we know that this term here is not going to give us a meaningful solution because no value of x can make that equal to 0. So the only meaningful solution is going to come from the expression 2 plus 3x is equal to 0. 3x is equal to negative 2, so it occurs that x is equal to negative 2/3. That's when we're going to get that inflection point. Just like we did earlier, though, we need the full coordinates for this, so we're going to go back into our expression for y of x. Y of x is equal to x e to the 3x, and we're going to plug in negative 2/3. So y of negative 2/3 is equal to negative 2/3 times e to the negative 2 in this case, because we have 3 times negative 2/3 leaves me with a negative 2, which leaves me with negative 2 over 3e squared. So the final coordinates for the inflection point are negative 2 over 3, negative 2 over 3e squared. Boom. A lot of calculus, we're almost there. Last part of this, okay? Last part, part E, they're asking us to, hence, sketch the curve, indicating any points from parts C and D and any intercepts with the x-axes. Okay, so this last part should be fun. Here's our set of axes. We know a few important things. We know from part C that there is a minimum occurring at the point -3, -1/3, and whatever that value of y is. We actually don't care because the command that the IB gives here is sketch, not graph. So we actually don't need to include any specific points. We just need to show the basic shape of the curve. So at x is equal to -1/3, we're going to have a minimum point, a negative value minimum point, something around here. Okay, which means that we know this curve is going to be increasing in both directions on this side. I'm not going to include this in, but we know that it's going to have that general shape. We also know a little bit further down that at -2/3, so a little bit more to the left, it's going to, not only having increased, it's going to reach an inflection point. An inflection point means, again, that instead of opening up in this kind of upward concave direction, the direction of the curve changes and it starts to be more concave down. So what we can expect to see is that this curve has this kind of shape at this point, it starts, oh, you know what, let's redraw this. This curve likely opens downward, downward, downward. Then when it reaches here, it starts opening more upward in this kind of direction, okay? And then we're gonna figure out, well, where does it go after this? To figure out where it goes after this, we need to figure out any intercepts. So if we take to figure this out nice and simply, remember this is x, hold on, undo, there we go, x e to the 3x. If we want to figure out where does this intercept the x-axis, we can just plug in 0. So when x is equal to 0, this is when it should be intercepting the y-axis, excuse me. Well, 0 times 1 equals 0, so it's going to cross this point right here, which basically means, was basically telling us that after this minimum point, it's going to make its way up all the way there. Since we know for a fact it doesn't have any more other local maximum or minimum because they would have come up in the first derivative analysis earlier, this is just going to shoot up, 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 up. And this is going to be the general shape for this curve. So we've sketched the graph of y of x is equal to x e to the 3x. There you have it, folks. Awesome, 21 marks, huge, you did super good. If you like this video and you want more, follow, subscribe, like, comment, all that stuff. More content coming your way.